sensitivity in measuring systems is defined as, okay, sensitivity, okay, it is used in the instrumentation, okay, instrumentation process, instrumentation, in instrumentation we will use this word, sensitivity. Actually it will tell the output response to the input, output response to the input. I think if you are familiar how we can measure the acceleration by using accelerometers, right? Accelerometers. We can measure acceleration, right? Means if I take example of a cantilever beam, see, if you want to measure the frequency of this beam, which is a cantilever beam, so what I have to do, I will place one accelerometer at this and I will connect to the some data acquisition system. There is a data acquisition system. So if I disturb this system, it will vibrate like to and fro motion about this mean equilibrium position, so that in data acquisition system it will process this data and it will give them my frequency value, correct, right? Frequency value in terms of hertz it will give. So before I am doing this measurement, I need to give the sensitivity to this accelerometer, right? So that accelerometer sensitivity I have to give S equal to some G value to the millivolts, okay? In output we are getting millivolts, we are giving some input as G, means G is acceleration due to gravity, means we are initially giving some 9.81 meter per second square acceleration and we are getting an electric unit in millivolts, okay, like typically 100 to 110 millivolts we are getting output, because this is one of the transducer, right? So that we are getting in electrical units, because some our fundamental units to the measuring units to the electrical units, it is the accelerometer sensitivity, okay? So this is the ratio of output response to the specified change in the input. If I change the input to some other value, it will detect the other value, okay, because this is also a sensor, working as a sensor, right? Okay, sensitivity is actually defined for the sensors or transducers, okay. Option 2 is the correct answer here. In sand molding system, the lower half of the molding box is called, see, in sand molding process, in metal casting process, we are placing the boxes, right? Okay, after that we are filling the sand in these boxes by doing ramming process. There is a boxes, after the placing boxes one over the over, and we are ramming it, right, using rammers and hammers. Actually we will call the power hammers we are using to ram the sand, right? So it is a parting plane, in between there is a parting plane, it will separate the two boxes, parting plane. Actually we are doing one by one. First we are ramming this sand, after that we are placing another ramming process done by the power hammer, and we are placing this box over the already ramming done on the box, okay. Means this box is, we will call it as a hoop box, it is a drag box, okay. Individually we are doing the ramming process, okay. So he is asking what is the lower half of the molding box. So this is a drag, right? So answer will be 2. Hoop is the top box, okay, it is a bottom box. Cheeks are which is a different thing, it is also used in metal casting. Cheeks are different thing. Actually cheeks are used to there is a pattern, okay, there is a pattern, and I need to take out if it is from top view, I am seeing the box. This box I am seeing from top, so that there is a sand, right? In between there is a pattern, right? After ramming process, I need to take out this pattern outside, right? So using these cheeks, I can use it to remove the pattern. Use it to remove the pattern from mold box. From mold box, okay? Sprue is the gating system actually. In gating system, sprue is the major element, okay? In gating system, this is the sprue. So your answer is drag. This is the correct answer. Option 2 is correct. Okay. Top box is called cope, bottom box is called drag. Okay. A sine bar is a precision instrument used for the measurement of. Okay. Options are linear distance between the 2 points, surface roughness and finish, angles, and gear to thickness. Sine bar actually it will look like this, right? There are two spherical balls, cylindrical rollers or spherical balls they are using. There is a Allen screws here. We are fitting to this body. And if you want to measure any taper angles of the surfaces, we are using sine bar. This is called sine bar. Sine bar. If you want to measure, see, using slip gauges, we are making the datum for this one. Here also we are using slip gauge. Okay. This is the angle made by this surface, right? My interest is to know this angle, right? So using the sine bar, I can calculate my angle. So, okay, using dimensions. See, this length is fixed, I know, because sine bar length is fixed. So using this datum, I can calculate this side also. Okay. If I apply the trigonometry, sin theta will become h by L, right? From here, theta I can find sin inverse h by L. This is the sine bar. Okay. Used for measuring the taper angles. Answer is 3. 3 is the correct answer. Okay. Pascal's law states that fluid at rest in a container. Okay. What Pascal's law will tell? If it is a fluid at a rest in a container, okay, fluid is at rest. Okay. If a fluid at rest in a container, if you take any point, if you take any element, the pressure will be same in all directions. Pressure will be same in all directions. Means if I take this element outside and if I draw the pressure distribution, the pressure will be constant in all directions. Okay. This is the hydrostatic law. Okay. We will see what is the option. Pressure is the highest at the bottom. Is it true? Correct. Pascal's law, it is not stating that pressure is highest at the bottom. See, if my Cartesian coordinate system is like this, right? X, Y. So if I go in vertical direction to the bottom, my pressure is high. But Pascal's law is asking, right? This is the pressure distribution. Dou P by dou Y, which is equal to P, right? This is my pressure gradient in Y direction. Okay. So this is not correct answer regarding Pascal's law. Pascal's law states that my pressure is always constant. Means in all direction my pressure is same with independent of direction. Correct, right? The pressure is transmitted uniformly at all points in the fluid. It is correct, right? It is uniformly distributed, right? Correct, right? So 2 option is correct. We will see. Third option also. Pressure depends on the velocity of the fluid. No, there is no relation with the velocity. Total energy remains constant throughout the fluid. See, this statement, total energy is asking, right? See, total energy of the fluid contains pressure energy plus velocity head plus datum head, right? It is in static condition, so velocity is 0. There is only piezometric head, right? There is a only piezometric head. Correct, right? In a static fluid, this piezometric head remains constant. Means total head becomes piezometric head, right? Piezometric head. If he is given piezometric head, this option also correct. Okay. For this question, this is a not correct answer because he is asking total energy, right? In total energy, velocity head is not there. Okay. Next question. Which of the following is not the assumptions on which Fourier's law of heat conduction is based on? Okay. Which is the not correct? I asking. Not correct assumption. We will see. The temperature gradient is constant, which is correct, right? dt by dx is constant. Means we are assuming that temperature is linear profile, right? Linear profile. Temperature profile is linear. And there is no internal heat generation also. This is also correct. And the conduction of heat takes place under the steady state condition. This is also correct. The heat flows in non-directional. Means heat flow is non-directional is asking. It is actually wrong statement. See, heat transfer by Fourier's law of heat conduction, we are writing minus k times AC dt by dx, right? Correct, na? So heat flux, I can write it as minus k times dt by dx, right? It is depending on the direction also, right? X. In x direction only we are measuring the flux. Correct, right? So it is not a non-directional quantity. It is a directional quantity actually. It is a directional quantity. It is a directional quantity. Directional quantity. Okay, it is a directional quantity. Why? Because see, it is for in x direction, right? In x direction, it is the Fourier law of heat conduction. Correct, right? If I take all directions, I will get minus k times dou t by dou x plus dou t by dou y plus dou t by dou z, right? In all directions. So I can write heat flux as minus k times grad of T temperature, right? I can write like this, right? It is a gradient, del operator. This is a del operator. So I can write the product of minus k times the del operator times T. So if any isothermal surface, if I take, the heat transfer will be normal to this surface, right? My heat flux is like this. So this is a direction. It is actually showing the direction, right? So it is a directional quantity. So option 1 is the correct answer for this one. This is for 3-dimensional. Okay, this is 3D. This is for 1D. Only x direction. Okay. Next question we will see. Which of the following is the non-contact type temperature measurement device? Okay, we'll see one by one. Thermocouple, which is actually a contact type, right? Which is contact type. Contact type. Where we are using two dissimilar metals joining one end and we are measuring the temperature at another end. So EMF will be generated, right? The EMF will be proportional to the temperature change. So we are measuring the change in the EMF which is proportional to temperature. So I can measure the temperature there. This is thermocouple is a contact type. Optical pyrometer is a non-contact type. Non-contact type, right? So non-contact type we are using in furnaces, boilers. We are using this optical pyrometer. Okay, by using the radiation. Okay. Answer is actually this only. We will see the other questions other also. Mercury in glass thermometer, which is also contact type, right? Resistant thermometer detector, which is also contact type. So actually, it is working on the Whetstone bridge, right? Whetstone bridge. Whetstone bridge. Whetstone bridge potential. This is Seebeck effect. Seebeck effect. So your option is 2. 2 is the answer. Next question. In forced vortex motion, the linear velocity v of the fluid particle is option A directly proportional to the radius or option 2 inversely proportional to the radius or option 3 independent of the radius or proportional to the square of the radius or. See, in forced vortex motion, we are giving the external energy means external torque we are giving to rotate the fluid, right? So tau is here we are giving, right, which is not equal to 0. In free vortex motion, tau equal to 0, but in it is a forced vortex motion, right? Forced vortex motion means this is the torque we are giving to rotate the fluid like this, torque. So that V velocity, forced vortex motion, right? Forced vortex motion. Vortex motion. Okay, forced vortex motion. So V equal to R omega times we are giving. Okay. So if you see clearly, velocity is directly proportional to R, right? Which is the linear variation, right? Okay. If I draw the velocity versus R graph, it is a linear variation. Like this it is going. So it is directly proportional to the radius R. If it is free vortex motion, my velocity will be inversely proportional to R, right? So my velocity and R is constant. If I draw the velocity versus my radius graph, velocity versus radius graph, I will get a rectangular hyperbola, right? Like this, because this is xy equal to constant type, right? Rectangular. At the center, if I come to closer, there is a mathematical discontinuity, right? There is a discontinuity. So that we should not operate at the center. We should go outside, away from the center. Then only my free vortex motion is possible. Okay? Because if I come to my radius is tending, if my radius is tending to 0, my velocity will become tending to infinity, right? This is not a correct value, because if my velocity is going to infinity means it is not feasible, right? So correct answer is A here. A is the correct answer. A is the answer. Okay. Next question. A plug gauge is an inspection tool used for primarily check the plug gauge. Okay. First we will see what is the ring gauge. After that plug gauge we will see. Ring gauge. Somehow we have manufactured some shaft. Okay. We need to inspect the shaft whether it is straight or round within the tolerances or not. We will see there is a ring gauge like this. There is a ring gauge. Okay. Use it to inspect the shaft. Okay. This is a shaft. Use it to inspect the shaft. It is ring gauge. What is plug gauge then? Plug gauge. By shearing operation, if I made any hole, okay. By shearing operation, if I made any hole, if my hole within the tolerance or not, how I can check? I have to use the plug gauge, right? Plug gauge is like this. There will be this gauge is there is a handle, okay? There is a handle. So I need to push this gauge inside the hole so that whether it is within the limit or not, it will tell. Okay, if it is not within the tell, we will not using this hole. Okay, for applications. So answer is the plug gauge, right? Plug gauge is used for the external diameter of the shaft. Option 1 is the correct answer. Okay, pitch of the screw thread means we will have some pitch gauges. Okay, we are using that one for pitch of the screw thread. This is also not correct. This is also not correct. This is also not correct. Flatness we are using by telesurf machine. Telesurf. Okay. Next question. Which of the following casting method uses wax pattern? Okay. In wax pattern we are using in investment casting, right? Wax pattern. Which is actually expandable pattern. Another name is expandable pattern. Expandable. In slush casting, we are using the pattern. Which pattern? Cast iron pattern, right? Over the cast iron pattern, we are using the phenolic resins and phenolic formaldehyde, alcohol we are using, right? In shell molding, also we are using metal pattern. Metal pattern. Okay. Metal pattern also we are using in shell molding. Continuous pattern we are using plastic. Okay, we are using plastic. Okay, in continuous casting, like thermocol also in casting, continuous casting process, thermocol. The moment when you pour the molten metal, thermocol will evaporate and it will travel throughout the pattern and it will like accommodate the like a pattern size. Okay, plastic we are using in continuous casting. Oh, for this question answer is 1. Option 1 is the correct answer here. Okay, investment casting or expandable pattern we are using, wax pattern. Next question, match the following. They have given part A and part B. It is actually a question from the industrial engineering, Hungarian method. Where we are using Hungarian method? In assignment problem, right? We are assigning the tasks to the different machines. And Vogel's approximation we are using in transportation problem. Okay, we will see the options. A stands for 2, right? 2. This option is not correct because A is 3, 3. Here 2. Both options are there. This is 4th option. And we will see Vogel's approximation is going to 4, right? A 4. B 4, right? B is 4. So that this is the correct answer. Okay, remaining Johnson's algorithm, actually we are using dynamic programming problem, right? Okay, this is the dynamic and the Johnson's algorithm assignment job sequence problem, right? Johnson's algorithm, sequencing and scheduling, these are using Johnson's algorithm. Okay, option is 4th option. The fundamental property of fluid is that option 1 undergoes a definite deformation under load. Okay, which is not correct. Actually, when you applied the load on the fluid will try to deform continuously, right? Continuously it will deform, right? So it is not definite, it is indefinite. Okay, and never regain to its original shape after the release of shear stress. Yes, it is correct answer, because when it is not like a metal, right? It is a fluid, so that when you apply the shear stress, fluid is continues to deform, it will not regain its original shape. We will see the other options also. Can resist the tangential stress at the static condition? No. In dynamic condition it is true. Okay, in dynamic condition it is true. In dynamic condition this statement is true. Dynamic condition, in dynamic condition which is true. Okay, 4th option has more compact molecular structure than solids. No, in solids there are more compact, right? Because cohesive forces are more in solids rather than the liquid, right? Okay, this is the correct answer. 2nd is the correct answer. This is also wrong. So 2nd is the correct answer for this question, because it will not regain its original shape after releasing shear stress, not like metals. Within the elastic limit, if I release the load, the metal can regain its original shape, right? So this is not the correct answer. The end products of the complete Osh tempering heat treatment cycle in medium carbon steel. See, Osh tempering actually we are doing not continuously, right? If I see the TTT diagram, there is a austenite region and there is a C curve, right? Like this. See, in Osh tempering process, what we are doing, we are cooling the austenite above the critical cooling rate, below the nose radius. Nose radius is typically 550 degrees centigrade, right? Below, above the, there will be a martensitic start line, martensitic finish line, right? So you will call this as a C curve. So here decomposition of the perlite 0%, here 100% decomposition of perlite will be there, right? 100% decomposition is there. So above the nose there will be a perlite, below the nose there will be bainite, right? Bainite. Okay, there will be bainite. Both are mixtures of alpha plus Fe3C only, but their microstructure is different. In perlite, microstructure is alternate layers of the alpha and Fe3C, right? Here there is a needle like formation of alpha in Fe3C matrix. Okay, this is a martensitic start line, this is the martensitic finish line, this is MS line, MF line. Okay, so if you want to do Osh tempering, we are cooling the austenite above the critical cooling rate, below the nose radius temperature, and we are maintaining this temperature up to some time, and it will touch the C curve, means TTT curve it will touch, and it will go to this region. So after this it will go to the bayonet region. Bayonet will form in arch tempering process. Okay, arch tempering process. Arch tempering process. See, in the arch tempering, it is a not continuous cooling process. Not continuous cooling process. What is the advantage of this stepped cooling process? This is actually stepped cooling process, right? We are rapidly cooling, and after that we are maintaining this temperature, right? What is the advantage of this process? Actually, we can avoid the surface crackings. Surface crackings will happen, right, due to sudden cooling. So that we can avoid in arch tempering process. And mar tempering process also we can avoid. So that's that phenomena, cracks formation. It will avoid. Arch tempering will avoid crack formation, surface crack formation. Surface crack formation. Okay, it will avoid the surface crack formation. Okay, answer is bayonet. Okay, martensite is the hardest phase of steel, right? Hardest phase of steel. Hardest phase of steel. When you will get this one, rapidly quenching means above critical cooling. This is the critical cooling rate line, right? This is the critical cooling rate line. So when you cool above the critical cooling rate, it will directly, if you can see up to room temperature, it will touch the MF line, right? So that you will get the martensite phase. Perlite, if you cool slowly, you will get perlite region. Okay, this is also over. This is also over. Austenite, this is the austenite phase, right? When you heated the steel above 723 degrees centigrade, you will get the austenite, right? So answer is, this is also not correct, this is also not correct, this is also not. Bayonet is the correct answer. Arch tempering answer. Okay, for this question 3 is the correct answer. I am not only giving the solution, okay, I am giving the all insights, okay, all other options also I am telling. Monel metal is an important engineering alloy primarily composed of, okay, monel metal actually a copper alloy which consists of copper plus nickel. Okay, monel metal. Okay, next question. Answer is 2, right? 2 answer. Next question. Malleability is the property of the material that allows it to be, see options, drawn into the long thin wires, hammer or rolled into the thin sheet without rupture, okay, and regain its original shape after load removal. Option 4, absorb shocks and vibrations effectively. See, this one is modulus of resilience or toughness, right? Modulus of this property is modulus of resilience, correct, right? So this one, regain its original shape after removal. This is the elastic limit, right? Elastic behavior. Elastic behavior. So this is also wrong. This is also wrong. Drawn into the long thin wires. Actually, it is a ductility property, right? Ductility property. Ductility property. So hammered or rolled into the thin sheets. Actually, malleability is the property of the material. It will turn into the thin sheets while rolling process. Okay, correct answer is 2. Option 2 is the correct answer. Questions are over. I hope this session will helpful to you. Thank you.